So previously, we looked at these reactions that allow us to have addition reactions on double bonds. It could be done on triple bond as well, but we were able to add chlorines, but we can also add the bromine. On the more substituted, less substituted carbon of the original double bond carbons in Markovnikov addition or in anti-Markovnikov addition. And we also can add in our needs. The OH is on the more or less substituted carbon in Mark and anti-Mark addition respectively. And this, I pointed out that it's going through one similar mechanism. And in this video, we're gonna look at the other type of mechanism. So, the common feature of the mechanism for those Markovnikov and anti-Markovnikov reaction was in the presence of double bond, the pi electron that's perpendicular to these sigma bonds, they are donating electrons to small atoms like hydrogen. So the key is the size of the atom, small size. So when the electron is given, hydrogen is not able to share those two electrons with the two carbons. Therefore, the hydrogen had to choose to hold the electron here or here. So you get the positive charge there, and we chose to form a bond here because the carbocation in this isomer is more stable. So this leads to the product. And in other case, this was radical when you had HBr or Cl with the peroxide. This generated halogens and was able to also form more stable intermediate radical on the more substituted carbon. So instead of hydrogen here, you get the halogen. Therefore, in next step of propagation step, this hydrogen end up coming here. So that's opposite to the regular case. This lead to the anti-Markovnikov, and so on. So the common feature of the mechanism was you are making traditional intermediate, having solid one bond formed first. So the traditional mechanism. So today's focus is on non-traditional in other words, bridged mechanism. One of the key factor is obviously size. So when you have a big atom for Lewis acid, you tend to form more bridged mechanism, but there could be other factors. So the first reaction we look at is when you have Br2. Br2 is non-polar compound, does not have partial charge, at least not permanent one. But you all know the nonpolar one can have an intermolecular interaction. As the size of the molecule increases, the intermolecular London force increases. That's because temporarily induced dipole, while they're moving around, the electron can create unequal distribution temporarily and causing dipole moment temporarily. When that persists, Br2 can run into the pi electron, so perpendicular pi electron here and here. They will be withdrawn to the partially positive. So moving this way. Then one of the key features to be good acid was to make a stable conjugate base in the product. So as you can see, when bromine accepts the electron, these electrons are able to move to this bromine, and bromine, using its big size, it is reducing repulsion of the electrons on the valence shell. Thus it lowers the potential energy. So overall the product becomes somewhat stable. So we know we form stable weak base, the conjugate base that's stable. But meanwhile, what happens to the bromine? Bromine is quite big, so these methyls here corresponding to that corresponding to that, they're all pushed up. The hydrogen located here is also going to be out here wedged and also pushed up when bromine approaches from the bottom. But due to the size of the bromine is able to share these two electrons in these two additional and this partial pi bonds. However, overall, they lose electron here to the bromine to make a bromide. So this turned into positive ion and having 2 electrons over 3 bonds. And then the stereochemistry changes this way. And also it's true that the bromine comes from the top and pushes all the groups down and create another isomer, stereoisomer. That's possible. Then in this form, you can see this carbon being secondary, the other one tertiary. So this partial bond is weaker and easier to break. Therefore, this weak bromide, being very selective, attack here, then break off this bond to create now full sigma bond here, pushing all the electrons here to the bromine shell, and then having methyl group still there. But due to the bromine, incoming bromine, these are pushed down as this leaving group goes away. Methyl group comes down here and here, and there you have your bromine forming full sigma bond. So here you have a couple points to make. One, because they form non-traditional bridged intermediate, the rearrangement is not possible, unlike the traditional mechanism always have potential to. So no rearrangement. Also, the nucleophile in the second step is approaching backside of this bromine. It appears to be almost leaving group because it is going away from the alpha carbon where the nucleophilic attack takes place. So this has SN2 type of mechanism with a backside attack. Third, always we check the stereochemistry. So as you can see, two bromines are located in anti position. So this is anti-addition. So please be careful. When you say anti-addition, we don't mean anti-Markovnikov addition, right? This is the geometry we refer to. Anti-addition, syn addition, which we'll see soon, refer to whether you have two groups that's added to double bond are in the anti location, or sometimes they could be on the same side. Then we will call that as a syn addition. Markovnikov was referring to connectivity, whether the nucleophile added to the more substituted carbon or less substituted carbon. So you call that anti-Markovnikov addition. If you have nucleophile ended up having bond with a less substituted carbon, or Markovnikov addition if the nucleophile comes into the more stable carbocation and form bond with the carbon that has more substitution. Okay, so we have a little variation, and you can apply the non-traditional mechanism to figure out what happens to this. This is very similar to the bleach structure. The difference is not chlorine, but you have a better leaving group bromine there. But those who are memorizing Br and the Cl as a good leaving group, you will see this as an exception. But you should not do chemistry based on memorization too much. Then you will see too many exceptions to memorize. So let's do chemistry with the principle and understanding. This reagent sometimes is given in the test as Br2 with water, because they do react and create this reactive form of chemical. So this is a typical situation when you have two reactants. You figure out their charge distribution and assign each chemical as a base or acid, and then draw a mechanism in order to figure out what you expect as a product. And I also, it's my habit, right, to point you to remember that there are other types of situation. You may not have two chemicals, but only one of them given, and then the product is given instead. So you need to compare the reactant and the product, figure out what the changes happened in the reactant, and then based on the changes you can figure out, you can connect it with the typical reagents and the mechanisms you remember. Or the third type, the hardest type, is you don't have any reactant information. We only have a product given. Then you have to do retrosynthetic, the new technique which I will cover soon, retrosynthetic approach. So like I said, you always look for the base, but in order to do it, you put charges, right? So the double bond has no charge. We all know the pi bond has a potential to act as a base if you have acidic chemical. So there you can see the bromine is partially positive, oxygen is partially negative, hydrogen is partially positive. So two potential acids are bromine and the hydrogen. And surprisingly here, the base attacks not the hydrogen, the bigger, easier target, bromine. So bromine is not acting as leaving group, but it's acting just like a carbon in the SN2 reaction, and you can break off. Then you know bromine is a big atom, so you expect to form non-classical bridged intermediate as you form the unstable hydroxide as a leaving group. So you know this is not a very good situation, right? So normally they give you acid as a catalyst. Then we should try again. So this is the basic oxygen, and you have a strong acid. They do react first, so you create this intermediate first. Then bromine will be more highly developing positive charge and become potential acid. The electron from pi is donated to the bromine and forming same intermediate, but now your leaving group is water. So you're good. So from here, you're waiting for base to give electron to the acidic, fully charged, positively charged intermediate. Then you have to choose which carbon you attack. As you remember, you attack the carbon that has a very weak bond. So the more substituted carbon doesn't need extra bond because they are stable with the charge, partial positive charge or full charge. So you're going to attack this carbon, but you come from backside like SN2. So what base you have? Water. So water attacks here, backside. No, this is not there anymore because of the acid. Then you break this off. Then your bromine moves over here, methyl group, and this methyl group pushed down by water, this as well. Water forms strong sigma bond, and you have water right there. And this is still very acidic, so it needs more electrons. So you use this oxygen lone pair of water as your base. Then it attacks here. The electron from the OH bond will be given to the oxygen, and making oxygen neutral and not acidic anymore, and you do create the final product. In anti form. But again, if you do have to discuss the stereoisomers, you know you have a same set of the intermediate in products when you have a bromine attacking from the top. Sometimes you come up with the same thing, just like this case, because you have two same groups on this carbon. But on this carbon you have a methyl and a hydrogen there, hidden one. So you actually have isomer there. But the isomer in this case will be enantiomer. The enantiomers have all same chemical properties, even spectroscopy properties. But you know, it's not always the case. So you have to know how to do it. Okay, before we end this video, let's have one practice question. this is the second type of a question I've been mentioning. You have one of the reactants and product. I don't care in this case, right, about the stereochemistry, but only paying attention to the functional group transformation. So functional group changed, and also you have a regio isomerism that you need to pay attention. So how would you approach this? Well, first you find out, right, the difference. So you compare, step one, you compare reactant and product. You compare, you see the carbon backbones are exactly the same. Difference is the changes you find out is you lose Br and gain OH, but you're not gaining on the same carbon. There is a rearrangement. You do it on this carbon. So there is changes of connectivity. So you have to connect with the typical reagents and memorize the reaction. So you need to connect with the typical reactions and reagents. So you lose something and you gain something else. It appears to be substitution, but we only know 3 substitution, and one of them is radical. It doesn't look like a radical, right? Radical reaction, usually we lost hydrogen. Instead of hydrogen, you put halogens, but it's not obviously the case. Then it should be either SN1 or SN2. If it's SN2, you would think, what do I need? You lose leaving group bromine in this case if you look at the product, and you gain OH. So you can think of OH as a nucleophile, and if you think of SN2, you need a strong base, so OH minus you think, but the typical mechanism of SN2 is when a strong base attacking on the alpha carbon and losing the bromine, then your nucleophile ended up sitting on this carbon, but it's not there. So you know SN2 is not your choice. So only thing left is SN1. And for SN1, you need weak base. So you cannot use OH. You have to use water for SN1. And you run SN1 mechanism, you usually run bond break and carbocation on the tertiary. And then if it's possible, you rearrange to the more stable carbocation, but you have to arrange to this carbon in order to put water there, eventually OH. But that's secondary. Why would the tertiary move to the less stable secondary? So you know even SN1 is not the case. That's when you need multi-step synthesis. We need to have a separate video on this, but how do you do it? Well, earlier video, I think we looked at the case where you have halogens, and then you can do SN2, SN1, but you can do same thing going through some other functional group. I hope you remember. If you have a Br, yes, you can form OH here easily, like we discussed earlier, but it's not easy to do this. That's the case here. So in this case, you have to go and say, how did we get this OH on the less substituted carbon? And we all know there's another option that was, remember from the double bond, you could go here, also go there, right? That's what we did. So if you come from here and getting there, we say that's Markovnikov addition. If you get there from the double bond, that is anti-Markovnikov addition. So to do anti-Markovnikov addition for OH, there's only one reagent you need to remember, right? In 2 steps. 1B2H6 with the THF. And the second step, you need OH minus with the peroxide. Yeah, you can have another case. You can put the bromine first as anti-mark with HBr and H2O2, and then replace the bromine to OH. You can do that as well. But anyway, you get the hint from this reaction you remembered. Then a remaining question is, how do we get this from that? So, which is basically, if the reactant is this, how do you get this product? It's the same situation like, you know, reactant going to the product, the kind of thing. So you need to do like a comparison. Oh, I lost the Br and the hydrogen CH3 turned into CH2 here. So this is losing atoms but not gaining anything instead. So it's just elimination. You can do E2, you can do E1, doesn't matter. So you know you can form this through elimination, then anti-mark addition of OH in 2 steps. So that's how you figure out, remembering some typical thing. So here you can see the carbon frame is there, and these are the additional groups, but it's still there. It doesn't make any difference. So you can simplify the whole question by looking at this area. It's the exact same thing here. So first you do elimination. Say you prefer E2, for example, because it's faster than E1. That's a tertiary bromine, and tertiary having elimination is not requiring so bulky group. Ethyl group is best, or isopropyl. Then you need strong base. Well, sometimes heating helps, and polar aprotic solvent such as a DMSO works well for E2. So there you will form double bond, but you need to form not Hoffman product. So that's why I want to control the size of the base. Hoffman product will give you double bond here, but I want double bond there, so I want Zaitsev product. So if you perform that, you get this double bond. Now we need to get there from here, which is this to that, anti-mark, okay, on the less substituted carbon. So here you need these two, right? So step 1 is there, so step 2, this, and in order to remove boron, instead put OH there, we need base with a peroxide. Then you can get there. So little application, and you'll see more extensive connections of the elementary reactions like this. So you need to work on the logical reasoning, on figuring out what you need, what changes happened in terms of the backbone, in terms of the functional group, in terms of the regio connectivity, also in terms of the modes of the reactions, anti-syn or stereochemistry, RS, you know, those things. So I'll see you next time, and keep practicing.